Labor costs historically account for nearly 48% of total production expenses in strawberry farming, driven by the meticulous handpicking required for delicate fruit. However, in the untamed ecosystem, the cost of harvesting the wrong berry is not measured in currency, but in biological risk and culinary failure. While agricultural drones now increase productivity by 50% using advanced recognition sensors to spot disease, the human forager must rely on onboard sensory tools. Today, we recalibrate your natural sensors to detect the subtle chemical and visual variances between the authentic Fragaria vesca and its deceptive biological counterpart. To appreciate the necessity of this precision, we must first examine the industrial scale of the genuine article. The global production of the modern strawberry is a feat of logistical dominance, generating approximately 1.3 million tons of fruit annually in the United States alone as of 2019. Within this massive agricultural engine, the primary friction point remains the staggering cost of human intervention. Industrial strawberry production faces a critical challenge in balancing the relentless demand for consistent quality with the heavy financial burden of manual labor. Expenses related to the workforce in commercial farming typically consume nearly half of the total production budget, creating an immense economic pressure to replace the variability of human observation with the infallibility of digital data. To mitigate these expenditures, the industry has turned its gaze toward the sky, deploying autonomous drones equipped with sophisticated multispectral sensors. These aerial units execute rapid, large-scale crop scouting, boosting operational efficiency by up to 50% compared to traditional manual inspection. By analyzing plant stress and hydration levels from altitude, these machines allow for a surgical approach to resource management. Irrigation efficiency improves by an estimated 20 to 30%, while precise pesticide application reduces chemical inputs by up to 40%. The result is a streamlined, optimized system where every variable is measured and every berry is accounted for to minimize chemical runoff and maximize yield. However, the human forager operates without this digital telemetry. When you step away from the commercial monoculture and into the chaotic biodiversity of the forest floor, the safety net of multispectral analysis vanishes. You must navigate a landscape where biological mimicry creates a high-stakes environment, relying solely on your own onboard sensory tools. Here, the cost function shifts dramatically. In the commercial sector, a harvesting error is a line item on a balance sheet. In the untamed ecosystem, the cost of misidentification is a distinct culinary hazard and the universal failure of the harvest. Nature has evolved its own form of deception, creating a nearly perfect visual duplication between the wild prize and its impersonator. Both species occupy the same environments, often thriving in disturbed soil, and both present a trifoliate leaf structure and red aggregate fruit that appear identical at a casual glance. The imposter spreads aggressively via runners, engaging in a silent competition for space and pollinators. While rarely toxic in small quantities, this berry presents a distinct culinary hazard. The fruit is technically edible but flavorless, composed of dry, mealy tissue that offers none of the sugars or esters found in the genuine article. For the forager, the penalty for error is the expenditure of energy for a reward that yields zero culinary value. This technological evolution in farming parallels the biological necessity for the forager to calibrate their own sensory instruments. Just as the drone distinguishes between a healthy plant and a stressed one using data beyond the visible spectrum, the human observer must learn to see beyond the superficial redness of the fruit. The first step in safe consumption is acknowledging that visual identification alone is a flawed metric in the wild. The presence of a red berry is merely a flag. It is not a confirmation of identity. From the macroeconomics of the farm, where millions of tons rely on precision data, the focus must now narrow to the specific taxonomy of Duchesnea indica, the invasive mock strawberry. To distinguish the prize from the parasite, one must abandon the reliance on simple color and examine the architectural blueprints of the plant itself. The primary subject of this structural analysis is Duchesnea indica, commonly known in the vernacular as the Indian strawberry or false strawberry. This distinct biological entity has successfully engineered a deceptive morphological similarity to the highly prized Fragaria vesca. To the uncalibrated observer, the immediate visual data suggests a successful find, as both genera produce a vibrant red aggregate fruit and exhibit a nearly identical trifoliate leaf structure. This biological camouflage is not merely an aesthetic coincidence, but a highly effective evolutionary strategy designed to exploit the vectors of seed dispersal, typically reserved for the authentic wild strawberry. The confusion arises from the shared architectural traits of the foliage and the fruit, creating a visual duplication often sufficient to fool uninitiated foragers primarily focused on color recognition. The operational theater of this botanical conflict spans a massive geographical footprint. The authentic Fragaria vesca thrives across United States Department of Agriculture hardiness zones 3 through 10, establishing a baseline range that the invasive mimic has aggressively infiltrated. This extensive overlap ensures that wherever the forager seeks the authentic prize, the imposter is likely present. Unlike the commercially cultivated hybrids that are confined to managed rows and controlled biological zones, these wild varieties engage in a silent, relentless competition for resources, pollinators, and physical space. The potential for misidentification is exacerbated by the fact that the Indian strawberry and the wild strawberry frequently occupy the same ecological niche, often growing within inches of one another on the forest floor. The presence of the mock strawberry often indicates a robust, disturbed soil environment where it can deploy its aggressive colonization tactic. Originally introduced to North America as an ornamental ground cover, Duchesnea indica has escaped the confines of managed gardens to become a formidable, invasive weed. It advances rapidly across the terrain using stolons, commonly known as runners, which root at the nodes to establish new, independent clones. This vegetative propagation allows the plant to form dense, interconnected mats that quickly outcompete native flora. The result is a pervasive biological carpet that dominates the understory, masking the soil surface and presenting hundreds of false targets to the foraging eye. While the consumption of Duchesnea indica does not typically carry the high penalty of acute toxicity found in other forest lookalike, it presents a distinct culinary hazard. The fruit is technically edible, yet it lacks the complex chemical profile that defines the strawberry experience. Instead of a burst of sucrose and floral esters, the consumption of the mock strawberry yields a watery, bland intake of dry matter. The texture is notoriously unpalatable, characterized by a mealy consistency often compared to styrofoam or compacted dust. Historical data and FDA reports indicate that while severe poisoning is statistically rare, there is a documented potential for allergic reactions in sensitive individuals. The primary consequence, however, remains the universal failure of the harvest, the expenditure of caloric energy to gather a food source that offers no sensory reward. Distinguishing the prize from the parasite requires a shift in observational protocol, moving beyond the superficial shape of the leaf to examine the reproductive structures of the plant. The most immediate and reliable visual indicator lies in the pigmentation of the bloom, a trait that signals the genetic divergence between the two species long before the fruit fully matures. The authentic wild strawberry, Fragaria vesca, consistently produces a flower with white petals surrounding a yellow center, a signature of its potential flavor. Conversely, the imposter Duchesnea indica displays a bright yellow flower, a chromatic warning inherited from its distinct ancestry. This divergence acts as a primary filtration step for the meticulous forager. To ensure a successful harvest, rather than a culinary disappointment, one must prioritize this specific chromatic signal. The systematic identification process begins long before the harvest, initiated by a definitive assessment of floral pigmentation. Before the plant invests energy in the production of fruit, it reveals its true lineage through the specific color spectrum of its petals. This indicator is absolute, a genetically hard-coded signal that is often overlooked by foragers who are singularly focused on the red allure of the berry itself. By shifting the observational focus from the fruit to the bloom, you establish a primary filter that saves time and mitigates the risk of collecting. The white petals act as a reflector of the available light spectrum, distinguishing the plant from the darker, chaotic greens of the forest floor. When scanning a patch of ground cover, this distinct white and yellow pattern confirms the presence of the target genus. It is a visual cue that has guided foragers for centuries, differentiating the prize from its numerous biological lookalikes. The consistency of this trait across the Fragaria genus makes it a reliable baseline for all subsequent verification steps. In stark contrast, the imposter Duchesnea indica, commonly known as the mock strawberry or Indian strawberry, betrays its identity with a vivid, bright yellow flower, This coloration is not an anomaly, but a direct result of its distinct genetic makeup. The yellow pigment permeates the entire petal structure, creating a uniform block of color that lacks the white signaling of the true wild strawberry. Where the Fragaria offers a contrast between a white rim and a yellow core, the Duchesnea presents a singular, monochromatic warning. This yellow coloration serves as a definitive marker for the non-flavorful, inedible look-alike, making it an easily distinguishable feature for those who know to look for it. The presence of yellow petals is an immediate invalidation of the site as a source of culinary value. This clear chromatic divergence, white flowers for true strawberries and yellow flowers for mock strawberries, acts as a binary switch for identification, much like a quality control sensor on an assembly line that rejects components based on color variance. The forager's eye must instantly categorize the patch based on this single variable. White signals potential flavor. Yellow signals the imposter. This visual test is considered absolute and constitutes the first foolproof elimination round in the identification protocol. By adhering to this rule, you preemptively filter potential harvest sites before expending the caloric energy required to kneel and inspect the fruit. If the ground is dotted with yellow blooms, the investigation ends immediately and the search moves elsewhere. The utility of this check is amplified by the persistence of these blooms. Because wild strawberries and their mocks often flower intermittently throughout the growing season, looking for the bloom provides a continuous reference point even when fruit is present. It allows for the rapid assessment of large swathes of vegetation. However, this is merely the first gate in a multi-stage security system. While the flower confirms the genus, it does not guarantee the quality of the specific fruit cluster. Once the fruit has developed and the blooms have largely faded or fallen away, the observer must then analyze the structural mechanics of its attachment, moving beyond the initial floral identification to examine the specific gravitational orientation of the berry itself. This vertical positioning is dictated entirely by the engineering of the fruit stem, specifically the peduncle. This component serves as the engineered link between the energy source of the plant and its reproductive payload, providing the next critical data point for verification. The physical posture of the berry relative to the ground is not random. It is dictated by the turgor pressure and the structural integrity of this connecting tissue. While subtle to the uncalibrated eye, the orientation of the fruit acts as a direct consequence of the species' biological design, revealing the fundamental architectural differences between the authentic harvest and its imposter. The true wild strawberry, Fragaria vesca, is characterized by a gravitational compliance that results in a distinct downward hanging habit. The peduncle of the edible species is constructed with a delicate cellular matrix that, while sufficient to transport nutrients, lacks the rigid lignification required to support the increasing mass of the maturing fruit against the pull of gravity. Consequently, the berry succumbs to its own weight, dangling toward the soil surface in a gentle arc. This dangling orientation effectively conceals the prize beneath the trifoliate canopy, creating a natural shield that may offer protection from specific pests or environmental desiccation. For the forager, this means the harvest requires active intervention. You must physically engage conservation. In sharp operational contrast, the mock strawberry, Duchesnea indica, engineers its reproductive display with a completely different set of structural parameters. This species holds its aggregate fruit upright, pointing aggressively toward the sky on a stiff, erect stem. The peduncle here is fortified against gravity, maintaining a vertical posture that thrusts the berry above the leaf line. This upright presentation transforms the fruit into a highly visible beacon, making the mock strawberry significantly more conspicuous to any passing observer. Unlike the hidden Fragaria, the Duchesnea is accessible without the need to disturb the foliage. From a distance, this makes the imposter immediately apparent, a trait that arguably aids in its dispersal by attracting the visual attention of different animal vectors that rely on line-of-sight foraging rather than scent or excavation. The difference lies in the tangible rigidity of the supporting column. When you examine the stem connecting the fruit to the central rosette, the distinction becomes palpable. The Fragaria stem is pliable, soft, and yields instantly to pressure, often bending without breaking. It is designed to flex. Conversely, the Duchesnea stem is characterized as rigid and unyielding, possessing a tensile strength that keeps the berry elevated even in wind or rain. It resists the downward pull, acting more like a localized pylon than a tether. This mechanical difference in the peduncle's structure is a reliable identifier that can be assessed even before the fruit is plucked. If the red object you are tracking sits proudly atop the leaves, staring back at the sun, it is displaying the classic posture of the Duchesnea. This architectural divergence effectively separates the passive mimic from the genuine article. A berry that points skyward, supported by a wiry stalk, is almost certainly the tasteless imposter, while the prize hangs low, requiring intimacy and effort to uncover. The mock strawberry relies on visibility and ease of access to propagate its lineage, whereas the wild strawberry relies on concealment and perhaps a more specific set of dispersers. Once the gravitational orientation has been established and the candidate sorted into the likely edible or likely imposter category, the identification protocol must zoom in further. The macrostructure of the stem gives way to the microtopography of the skin, bridging the gap between the gross anatomy of the plant and the fine details of the fruit. The investigation now descends to the level of surface topography, forcing the observer to engage with the distinct architectural differences that govern the exterior of the fruit. While the chromatic analysis of the bloom and the gravitational assessment of the stem serve as long-range indicators, the definitive separation of the species often requires a micro-inspection of the skin itself. To the naked eye, operating at a standard distance, both biological units appear as red, conical aggregates dotted with seeds. However, a closer examination reveals that the placement of the achenes, the botanical term for the actual dry seeds, varies significantly between the genera, functioning as a tactile braille that reveals the plant's true lineage. The surface of the mock strawberry, Duchesnea indica, is defined by a distinct lack of integration between the seed and the fleshy receptacle. Here, the achenes protrude aggressively from the red skin, sitting atop the fruit like external rivets on an industrial casing. This physiological arrangement creates a distinctly bumpy texture that is immediately perceptible to the fingertip. When you run a thumb across the surface of a Duchesnea specimen, the sensation is rough and resistant, similar to the friction of fine grit sandpaper. This structural rigidity is not merely a surface detail, but an indicator of the internal composition of the berry. The protrusion of the seeds correlates with a lower water content in the surrounding tissue, resulting in a fruit that remains firm and unyielding even when fully distinct. This architectural hostility translates directly to the culinary experience. The tactile warning provided by the protruding seeds is a precursor to the mouthfeel, which is universally described as a failure of texture. Because the Duchesnea lacks the cellular capability to retain significant moisture, the consumption of the fruit yields a dry, mealy sensation that is significantly lacking in juice. The texture is frequently compared to styrofoam or compacted dust, a gritty endurance test that offers no resistance to the tooth but absorbs moisture from the mouth rather than replenishing it. The berry maintains its structural integrity until it is mechanically pulverized, refusing to break down into the pleasurable, liquid-dense mash characteristic of edible fruit. This dryness serves as a final physical barrier, confirming that the energy expenditure of the harvest will not be repaid in hydration or caloric density. In direct opposition, the authentic wild strawberry, Fragaria vesca, engineers its surface for a completely different interaction. The achenes of the true genus are found on a nearly flat surface, sitting flush with the skin or slightly sunken into the receptacle as the fruit matures. This creates a smoother, more aerodynamic profile where the seeds do not interrupt the tactile scan. The skin feels uniform and polished, lacking the abrasive bumps of its invasive competitor. This structural choice reflects the biological priority of the Fragaria to present a soft, palatable package that invites consumption by specific dispensers rather than resisting it. The most telling variable in this tactile analysis is the fragility of the object. When handled, the wild strawberry exhibits a delicate constitution. It is soft to the touch and easily bruised by even moderate pressure. The cellular matrix of the Fragaria is highly turgid, pressurized with water and dissolved sugars. Upon the slightest compression, the fruit wall collapses, releasing a visible smear of red juice onto the skin of the forager. This lack of structural resistance is a hallmark of the edible variety. While the mock strawberry feels like a rubberized synthetic prop that bounces back from a squeeze, the wild strawberry surrenders immediately, signaling the presence of a high-moisture internal payload. Therefore, the manual verification process acts as a rigorous filter. If the specimen under inspection feels hard, dry, and covered in protruding bumps that snag the ridges of the fingerprint, it is undeniably the deceptive Duchesnea. A berry that is firm enough to roll between the fingers without damage is a berry that will offer the texture of gravel. Conversely, a specimen that feels smooth, yields softness, and threatens to stain the fingers with juice is the target harvest. Yet, while the architecture of the skin provides strong evidence of edibility, visual and tactile data are insufficient for absolute certainty. The final confirmation requires the activation of a deeper molecular sensor, the ability to detect the invisible chemical signature released when those delicate cells are finally ruptured. The definitive separation of the target species from its biological mimic requires a transition from the visual spectrum to the chemical one. While the tactile feedback of the achenes and the gravitational posture of the stem provide strong indications of the specimen's lineage, the olfactory confirmation of the fruit remains a biological code that is impossible for the imposter to replicate. A berry may present a flawless visual facade, displaying the requisite redness and conical shape, yet contain none of the sugars or esters that define the strawberry experience. Here, the investigation moves from the macroscopic architecture of the plant to the molecular composition of its cellular fluids. The final verification step is a destructive test, sacrificing a single unit of the harvest to ensure the validity of the collection. The standard operating procedure for this analysis is known as the crush test. This protocol involves isolating a single specimen from the patch and subjecting it to controlled mechanical stress. By gently compressing the fruit between the thumb and forefinger, you trigger a deliberate cellular disruption. This action ruptures the vacuolar membranes within the tissue, forcing the release of internal vapors into the immediate atmosphere. It is a critical diagnostic moment where the plant is forced to reveal its true metabolic investment. Visual mimics can copy the shape and color using relatively simple pigments and growth patterns, but the synthesis of complex flavor compounds requires a significant biological expenditure that the imposter species effectively bypasses. When a true Fragaria vesca undergoes this structural collapse, the result is immediate and potent. The ruptured cells release a complex cloud of volatile organic compounds, or VOCs, that hit the olfactory receptors with intense sweetness and distinct floral notes. This signature aroma is not accidental. It is driven by a unique, concentrated profile of specific esters, pheromones, and terpenes. These compounds are synthesized by the wild strawberry to signal ripeness to specific animal foragers, acting as a chemical beacon in the dense undergrowth. Even a fruit as small as a fingertip contains a concentration of these aromatics sufficient to be detected instantly upon the breach of the skin. The release of this perfume is the plant declaring its nutritional density, confirming the presence of the sugars and acids that make the harvest viable. In stark contrast, the mock strawberry Duchesnea indica reveals its deficiency the moment the skin is broken. When subjected to the same compressive force, the specimen emits little to no discernible scent. The biological machinery of the Duchesnea is calibrated for rapid vegetative spread rather than the production of expensive fruit aromatic. On occasion, the observant forager may detect a faint, watery odor, often described in technical field reports as reminiscent of cucumber or flat vegetation. This absence of a strong, sweet strawberry perfume is a critical data point. It indicates a hollow biological promise. The lack of aromatic volatility directly correlates with the lack of desirable flavor. The mock berry is constructed primarily of water and cellulose, devoid of the complex flavor chemistry found in the target genus. This lack of scent acts as the final disqualifier. If the vapors released during the crush test are neutral or vegetal, the fruit is confirmed as the bland imposter. There is no middle ground in this chemical analysis. The true wild strawberry does not produce a weak signal. Its aroma is unmistakable and robust. Therefore, the presence of that specific, intense perfume serves as the final, undeniable proof of edibility. With the sensory checklist complete, the process of identification is fortified against error. The integration of visual data from the bloom, structural data from the stem, and chemical data from the aroma allows the forager to proceed with the harvest, effectively replicating the precision of agricultural sensors in the wild. This systematic approach ensures that the final selection is not a matter of chance, but the result of a calculated elimination protocol. The distinction between a culinary delight and a biological disappointment rests on the strict application of this three-step validation process, while industrial drones utilize multispectral analysis to boost productivity by 50% and reduce pesticide inputs by 40%. The forager achieves comparable fidelity through biological calibration. By rigorously assessing the chromatic divergence of the white bloom, the gravitational compliance of the stem, and the molecular conformation of the aroma, you effectively replicate the precision of high-tech agricultural systems. The journey from the automated facility to the forest floor demonstrates that your onboard systems are now successfully calibrated. Through science and observation, you possess the precision required to navigate the wild harvest. If you enjoyed this video, don't forget to like, share, and subscribe to the channel.